Hello everyone, welcome you all at Loki's Unlimited Study Zone. So in the chapter of alternating current, our today's topic is average power in the RLC series circuit. So average power. Let us the alternating EMF applied in an RLC circuit is given by E equals to E naught sin omega t. Yes, write this equation. So students, we are talking about the power. Actually, power is given by P equals to power equals to voltage multiplied by current. So till now we have learned only about the DC power, but now we have to deal with the AC power. So instantaneous power at any instant, instantaneous power is given by the formula P equals to V at any time t multiplied by I at any time t. Okay. So we have the EMF or voltage at any instant equals to E naught sin omega t. Suppose your current is having some phase angle with the phase of voltage. Consider the equation for the current equal to I naught sin omega t minus 5. So if alternating current developed lags behind the EMF by an phase angle phi, then I equals to I naught sin omega t minus 5. You can also take I equals to I naught sin omega t plus phi. No problem at all for this situation. Okay. So I equals to I naught sin omega t plus phi. Otherwise, I equals to I naught sin omega t minus phi. Clear or not? Okay. Now, power power is equals to rate of consumption for electrical energy. So here the power is varying instantaneously. So we will use the formula P is equals to average power is given by P is equals to dW by dt, dW by delta t, and instantaneous power becomes equals to dW by dt. Fine. Yes. So this is for average power and this is for instantaneous power. P is equals to dW by dt. So it can be given by E into I. The value of E equals to E naught sin omega t and value of I equals to I naught sin omega t minus phi. Clear? Now open the relations for sine omega t minus phi. We have the formula from trigonometry sine A minus B equals to sine A cos B cos B minus cos A sine B. Clear? So here it will be equals to sine omega t minus phi minus phi. It can be written as sine omega t cos phi minus cos omega t sine phi. So you can write this equation like this. Okay. Sin omega t cos phi minus cos omega t sin phi. Now, if you open this sin omega t, this sin omega t get multiplied with by this sin omega t. Here you will have I naught sin square omega t cos phi minus E naught I naught sin omega t cos omega t sin phi. Clear? Hmm. So E naught I naught sin square omega t cos phi minus E naught I naught. What you have done? See, E naught I naught sin omega t cos omega t. If you multiply here with 2, you should have multiply here with also 2. Clear or not? Because 2 and 2 will be cancelled. And the formula for 2 so sin omega t and cos omega t will give you sin 2 omega t. Why? Because sin 2 theta equals to 2 sin theta into cos theta. 2 sin theta into cos theta. So in the place of 2 sin omega t cos omega t, you will have sin 2 omega t. Clear? Because this omega t is working like theta. So 2 sin theta cos theta is equals to sin 2 theta. Clear? And sin phi remains here as same. If the instantaneous power is assumed to be remain constant for a small time dt, then the small amount of work done in this time dw. Now, simply you have this expression as dw by dt. Okay. So dw equals to this dt will goes up and this will become dw equals to E naught sin square omega t cos phi minus E naught I naught upon 2 sine 2 omega t cos phi dt. Clear? So the work done over a complete cycle may be given by, work done for a complete cycle is given by, just integrate this, so you will have the total work done. So integrate within the limit 0 to time period. For one complete cycle, you have to integrate it over 0 to time t. So take the integration limit 0 to time t e naught I naught sin square omega t cos phi dt minus e naught I naught by 2 sin 2 omega t sin phi dt. Clear, beta? Now, E naught, I naught, and cos phi will be constant because they do not contain the term of a small t. As t is the variable here, so the only term that is a variable is equals to sin square omega t dt, and the value is going from the t's from 0 to capital T. Clear? Similarly, I naught into sin phi, it will be taken out, I naught sin phi, and sin 2 omega t 0 to t. Clear? Yes. In the lecture, in the that one, the average value, sorry, the RMS value, during the derivation of RMS value, I told you the average value for the sin square omega t equals to t by 2. Yes or no? It was equals to t by 2. So just place, instead of solving this one, you have to place simply this is equals to t by 2. So this will become e naught I naught cos phi into t by 2. E naught I naught cos phi into t by 2. And this is the one complete sine function, and for a sine complete function, its average value for a complete cycle equal to 0. So here just you have to place 0. So you have the work done equals to, for one cycle your work done equals to E naught I naught cos phi into t by 2. Clear? Average power is given by average power of the RLC circuit over a complete cycle. Power is equals to work upon time, is small t. Okay, this is average power. For a complete cycle, power equals to 1 upon t, because for a complete cycle, time period equals to capital T. Now, if you divide it by t, you will have, if you divide it by t, so W upon t equals to, if you take this t this side, so the remaining term will be E naught I naught cos phi upon 2. Clear or not? Cos phi upon 2. Okay. So, you can write this 2 cos phi upon 2. So you can write this 2 like under root 2 into under root 2. In the place of a single 2, you have to just t and t get cancelled. So 2 will be there. So make root 2 as under root 2 into under root 2. Clear? So this 2 becomes under root 2 into under root 2. So 1 root 2 appear as a denominator of E naught, and 1 for the I naught, and cos phi will be here. So this is equals to P average power equal to ERMS IRMS cos phi. Got it? So this is the derivation for average power. Okay, students. So for a complete cycle, we have got the relation for the average power. PAV equals to VRMS multiplied by IRMS multiplied by cos phi. Clear? VRMS into IRMS equals to cos phi. We have the phasor diagram. We know for a LCR series circuit, this is the phasor for current, and this is the phasor for voltage. Okay. Hmm. If we complete this triangle, we have this voltage as VR. This is the resultant voltage VR. Fine. And this is V, that is equals to I into Z. Now what is cos phi? Cos phi from this triangle equals to base upon hypotenuse. So base equals to the VR, and hypotenuse is the resultant voltage V. Clear? So VR may be written as I into R, and V equals to I into Z. I and I get cancelled out. So cos phi becomes R by Z. Clear? So this is the value for cos phi. This cos phi is called power factor. Power factor. Fine. Note this. Okay, so hence average power over a complete cycle in an inductive circuit, okay, in an inductive circuit is uh, is the product of the RMS EMF and RMS current and cosine of the phase angle. Yes, this is called cosine of the phase angle. Why we are saying here that RMS, the average power for over a complete cycle in the inductive circuit? Because you see here, we have taken the V equals to V naught sine omega t. Okay. For the above derivation, we have taken the value for voltage equals to V naught sine omega t, and I equals to I naught sine omega t minus phi. Clear? Means the voltage is leading from the direction of current. Here the voltage is leading the current with an angle phi. So this is inductance dominated circuit, because in inductor current will be leading position. So here this circuit is, that's why it is called inductive circuit. Okay. Yes. So this circuit is said to be inductive circuit, but you can apply this formula for any type of circuit. It is not necessary that the circuit should be inductive only. So the power is the product of the RMS EMF, RMS current, and the cosine of the phase angle between the voltage and current. The above relation is applicable to all the AC circuit. Yes, I just said whether we have developed this circuit, this relation from the inductive case, but this formula is applicable for every type of circle. Clear? So this formula is applicable for every type of circle. Cos phi and Z will have appropriate value for different circuit. Yes, cos phi and Z will have different values for the different type of circuit. Let us see for the value of cos phi. Yes, we have cos phi. We just see in the cos phi equals to R by Z. Okay. For a purely resistive circuit, Z equals to R. In a purely resistive circuit, only one circuit component is there. So Z equals to R. Fine. So cos phi equals to R upon R. So this is equals to 1. Means cos power factor equals to unity. Clear or no? One thing also, during the pure R circuit, when a circuit containing only pure R with a AC, we know the applied the flowing current and the voltage are in the same phase, VR and current in the same phase. So angle of phase equals to 0 degree. So cos phi so equals to cos 0 degree, and cos 0 degree equals to 1. Clear? First case. In second case, when pure inductor was there, so during the pure inductor case, here you have to apply the EMF. During the pure inductor case, the voltage across the inductor at 90 degree from the current. So here the angle equals to 90 degree. So cos phi equals to cos 90 equals to 0. Clear? Yes. Because cos phi equals to R by Z. During the case of inductor, resistance equals to 0 and Z becomes only XL, inductive reactance. So it will equals to 0. Clear or not clear? Third case, for a pure capacitance, again R equals to 0. Okay. Again R equals to 0, and your condition will be like this. Your VC will be lagging behind the current with an angle 90 degree. So again cos phi is equals to cos 90 degree. So here equal to 0. Clear? By another view, cos phi equals to R by Z. During the pure resistance, no resistance was applicable, but in the place of impedance, there will be XC. So 0 upon XC equals to 0. Clear? Yes. Yes. Talking about energy in a pure resistive circuit, we have the energy relation power equals to Vrms into Irms cos phi. So cos phi becomes 1 in the case of purely resistive circuit. So here it will be equals to 1. So your power will be Vrms into Irms. Clear? So average power will be equals to here Vrms into Irms. Then here average power will be equal to 0 because cos phi equals to 0. So average power for a complete cycle will be 0 here for a pure inductive circuit. Once again here cos phi equals to 0. This means average power equals to Vrms into Irms into cos phi. But cos phi here equals to 0 as phi equals to 90 degree. So average power in the pure capacitor is also equals to 0. Fine. You see. So for a pure resistive circuit, here Z equals to R and cos phi equals to 1. For a pure inductive circuit, Z becomes equals to XL and cos phi equals to 0. For a pure capacitive circuit, Z equal to XC and cos phi equals to 0. For a LC's R circuit, Z equals to under root R square plus XL minus XC whole square and cos phi equals to R upon Z. Clear? For in a RL circuit, Z becomes under root R square plus L square and cos phi equals to R by Z. For a RC circuit, Z equals to under root R square plus XC square and cos phi equals to R by Z. Moreover, you can write R upon under root R square plus XL square. And here this will be equals to R upon under root R square plus XC square. Clear? In a LC circuit only, your impedance equals to only because no resistance will be there. Place R equal to 0. So you will have XL minus XC ka whole square that is equals to XL minus XC and cos phi equals to 0. Why? Because as R equal to 0, so cos phi equals to R by Z. Placing R equals to 0, here you will have cos phi equal to 0 means angle of phase equals to 90 degree. Got it? Okay, students, our next topic is power factor of an AC circuit. Power factor. So far we have seen the power factor is given by cos phi. This is equals to R by Z. Cos phi equals to R by Z. So referring to the theory of the power factor, we know that the average power in an AC RLC circuit is given by P equals to ERMS IRMS cos phi. Here P is called the true power. Okay, P is called the true power. ERMS and IRMS are called ERMS into IRMS is called the apparent power or virtual power. See here, two things are there. If you taking cos phi into the account, then this P average is called true power VRMS into IRMS into cos phi. So this is called true power. Clear? When you're taking cos phi into account. But by the formula of P equals to VI, if you only writing P is equals to VRMS in the place of V, there is VRMS and in the place of I, there is IRMS. Then this type of power is called, power is called apparent power or virtual power because only this much formula is not sufficient to give you the power. So this is called apparent power or virtual power. This is the formula for apparent power or virtual power. Fine. Yes. Apparent power or virtual power. And cos phi is called power factor of the circuit. So this cos phi is called power factor of the circuit. So if you divide apparent power if you divide the true power with apparent power. So P true upon P virtual. Virtual means apparent. So we have got the P true equals to VRMS into IRMS multiplied by cos phi, right? And we have got the virtual power as VRMS into IRMS. Now VRMS cancel, IRMS cancel. So here it is equals to cos phi. So what is cos phi? This is called power factor. So power factor being the ratio of the true power with virtual power. Okay. So it is the power factor cos phi is the ratio of the true power with virtual power or apparent power. By the diagram it is given by, we have seen uh, it is equals to cos phi equals to base is given by VR resistive voltage upon net voltage. You can also take it E naught or E naught or E. So VR resistive voltage, the peak value of the resistive voltage is given by I naught into R, and the peak value of the E naught is given by equals to I naught into Z. Okay, I naught cancelled out, so cos phi equals to R by Z. Clear? Yes. For a non-inductive circuit, when there is non-inductive, so non-inductive circuit XL equal to XC. For a non-inductive circuit XL equal to XC, power factor is equals to cos phi, that is equals to under root R square upon R square, that is R by R equals to 1. Yes, non-inductive means when there is no inductance, then power factor equals to cos phi equals to R by Z. Okay. So you know pure resistance is R and Z is also R. So R and R getting cancelled out, the power factor becomes unity. Yes. So if cos phi equals to 1 means phi equals to 0 degree. This is the maximum value of the power factor. Yeah, obviously cos phi having the maximum value 1. So this is the maximum value of power factor. Clear? Hmm. In a pure inductor or in a pure ideal capacitor. Yes, I have talked about this during a pure inductor and pure capacitor. See here. During a pure inductor or pure capacitor, there is an angle of 90 degree. So cos 90 becomes 0. Cos 90 becomes 0. So power factor also becomes 0. Okay. So power factor equals to 0. And this time average power consumed in a pure inductor and ideal capacitor. Okay. Pure inductor or pure capacitor. Whenever cos phi equal to 0, it will give you the value 0. Means during a full half cycle, your power will be consumed equals to 0. Power consumed, average power during a full half cycle equals to 0. Fine. So in actual practice, we do not have ideal inductor or ideal capacitor. Therefore, there does occur some dissipation of energy. But in practical situation, if we have sorry, in ideal situation, if we consider a ideal capacitor or ideal inductor, then surely the power will be 0. Okay, in a complete half cycle, power will be 0. Clear? Okay, students. So see the numerical. An inductor and a bulb are connected in series to an AC source of 12 volt 50 hertz. 2 ampere current flows in the circuit and the phase angle between voltage and current is pi by 4 radian. Calculate the impedance and inductance of the circuit. So two things you have to find. One is impedance and another is inductance. So VRMS is given by 12 volt and frequency is 50 hertz. Angle of phase is pi by 4 and IRMS equals to 2 ampere. So first impedance is equals to VRMS upon IRMS. So that we have calculated is equals to 6 ohm directly by dividing this. Power factor equals to R by Z. So R becomes equal to Z cos phi. Place the value of R and phi. Cos 45 equals to 1 by root 2. So you have R equals to 3 root 2. Now you have the formula Z equals to, for RC circuit, Z equals to under root R square, sorry, RL circuit plus XL square. Squaring both the side, you will get Z square equal to R square plus XL whole square. So XL square equal to Z square minus R square, you will get 3 root 2 ohm. And finally, the XL capacitive, sorry, inductive reactance equals to 2 pi FL. So for L, you have XL equals to 3 root 2. Now place the value. For L, take it this at denominator 2 pi F. So 3 root 2 upon 2 pi F equals to becomes 3.5 millihenry. So this is the numerical related to the LR circuit. Now moving in a numerical for LC circuit. Yes. A capacitor and a resistor are connected in series. So there is a capacitor along with a resistor is connected. So this is C and R RC circuit. And its the impedance is given by Z equals to under root R square plus XC square connected with the AC source. If the potential difference across C R is equals to 120 volts, so this is the VRMS applied. 90 volt, 120 volt comma 90 volt, sorry, these are across C and R. Okay, so this is VC and this is VR. VC equals to 120 volt and VR equals to 90 volt, and the amount of current to the circuit, that is IRMS from the series circuit, equals to 3 ampere. First you need to find the impedance, quite simple. Okay, second, then power factor of the circuit. Two things you have to find. First find the impedance, then power factor. So see student, how to do this question. We have given VC equals to this, VR equals to this. So first find the VRMS, the net voltage. As VC and V are perpendicular, so both the voltages are perpendicular, so the resultant voltage will be lying somewhere here. So it is by Pythagoras theorem we have got it is equals to 150 volt. Now IRMS equals to VRMS upon Z. So Z becomes VRMS upon IRMS. So we have got also Z, the value of Z equals to 50 ohms. This is first part. Now VR is equals to VR equals to I into IRMS. Sorry, here it should be equals to VR equals to IRMS into R. So R equals to VR upon IRMS. VR is given here 90 and IRMS as 3 ampere. So this is equals to 30. Now cos phi equals to simply R by Z. This is equals to 0.6. So simple. Fine. Okay. Now, student, our new topic is choke coil. Actually, in our syllabus, one topic is next topic is after power factor, power in the AC circuit, then power factor, then it is wattless current. So, to understood this wattless current, choke coil is very important because choke coil is the practical application of wattless current. Okay, choke coil is the coil where we use the wattless current. Okay. So let us understand choke coil. Choke coil is simply coil having a large inductance and very small resistance. You see, it is practically impossible to make a coil that having only inductance. Okay, so practically we cannot got a coil that only having inductance but no resistance. But practically we can estimate a coil that having a very large value of inductance and it is very less amount of resistance. So, so this coil is this practical coil is considered, or you can say it is an approximation of the an ideal type of coil. So how to make this coil in which resistance is very small. So you know the impedance equals to under root XL square plus R square. But XL is very greater than R because the inductance is quite high and resistance is very less. So you can write it is disappear. We can neglect this R. So only you will have XL square. So impedance will be equals to like XL. Fine. Okay. So in this situation, this circuit is behaving like a purely inductive circuit. In that case, purely inductive circuit, the VL will be 90-degree leading phase from the current. Okay, so angle equals to 90-degree, phase angle equals to 90-degree, and power becomes zero because P equals to VRMS IRMS cos phi. So by the average power, P AV equals to VRMS into IRMS into cos phi. So cos phi because of cos 90 becomes zero. Choke coil. Choke coil is simply a coil having a large inductance but a very small resistance. Construction. Choke coil is made by a thick copper wire to reduce its resistance. Yes, there should be thick copper wire. Why? Because R is inversely proportional to A. If area will be more, resistance will be less. That's why you're taking a thick copper wire. Fine. To reduce its resistance, it is wounded on a plated soft iron core to increase its self-inductance. Yes, this is a plated means first you have to cut the slices of this soft iron core, then laminate each of the part, then join them. So this will increase its self-inductance. Principle: at most places, the household electric power is supplied at 220 volt 50 hertz. In such sources directly connected to the mercury tube, the tube will be damaged. To reduce the current, a choke coil is connected with a series of the tube. Power consumed in the AC circuit P equal to ERMS IRMS cos phi equals to 0. So the P, because of pure inductance, phi equals to pi by 2 and the power equals to 0. Hence, the advantage of using choke coil is to reduce the voltages that inductor does not consume power. Hence, we do not lose electric energy in the form of heat. As like there is a bulb first, okay. Hmm. You know, in AC supply, there is a strong fluctuations of supply, so that this can be damage your bulb. But you know the property of inductor, it always opposes the flow of current. Okay, it always opposes a change in current. So by this property, your bulb may be safe. So and using this coil, as there is no power dissipation by the concept of phi equals to pi by 2, your power loss equals to 0. Fine. And without of any dissipation of energy, your coil will work here. So this is called choke coil. Now next concept is wattless current or idle current. Yes, wattless current or idle current. Okay. So concept is like this. See, this is your uh, voltage, phasor of voltage, okay? And this is your current, clear? Your net current. Okay, so if phase angle is phi from the voltage, then you can resolve the two component of current. One is that is along the voltage applied, so that will be equals to I cos phi. Clear or not? And another one that is the perpendicular in phase with perpendicular to the voltage, that is equals to I sin phi. Clear? Now check the power consumed by the component I sin phi. What is the effective angle of the I sin phi with the voltage? For I sin phi having an angle with voltage equals to 90 degree. Clear or not clear? So if you calculating the power consumed by this component of current, so P average equals to Vrms into Irms. So in the place of Irms here, it is equals to I sin phi multiplied by cos phi. Okay, so angle cos phi is equals to cos 90. Cos 90 becomes 0 means average power equals to 0. The unit of power is equals to watt. So the wattage here, the wattage consumed here equal to 0. So no wattage will be consumed here by the this component of current, that is called I sin phi. So that's why this is wattless current. Clear or not clear? Wattless current. So simply, what is wattless current? I sin phi is the wattless current. Okay. Okay. The current in which the current which consume no power. Yes, the current which consume no power for its maintenance in the circuit is called wattless current. We know that the average power over a complete cycle in the inductive circuit is given by V equal to ERMS IRMS cos phi. Okay, otherwise you can take it VRMS IRMS cos phi, no issue. Okay, applied voltage sometimes it may be VRMS or ERMS as per your choice. In a particular circuit, suppose ERMS leads IRMS by an angle cos phi. So here you have this is in IRMS, clear, and this is your ERMS, clear beta. Now check your ERMS here is leading with an IRMS with a angle phi, clear. So you can resolve the two part of IRMS first in the direction of uh, ERMS. So that will be equals to your IRMS cos phi. Clear? And one may be the perpendicular direction of this IRMS cos phi. So the perpendicular component is equals to IRMS sin phi. IRMS sin phi. Clear? So as this angle is phi, so the angle that adjoining the phi is called cos component, and that is another one is called sine component. So this is equals to IRMS sin phi. Clear? Okay, so IRMS can be resolved into the two rectangular component. Here we have resolved this IRMS into the two rectangular component. One is cos component, another one is sine component. Now check what is the effective angle of this sine component with this ERMS. Check here the angle equals to 90 degree. So if you find the consumed power by this component, that will appear as 0. So IRMS can be consumed into the two rectangular component. First IRMS cos phi, that is working along ERMS, and IRMS sin phi, that is perpendicular to ERMS. Okay. Thus IRMS is the vector sum for the two perpendicular component IRMS cos phi and IRMS sin phi. Everyone knows the sine and cos component having a result of the complete vector. As the phase angle between ERMS and IRMS cos phi, okay, the average power consumed per cycle during by the component IRMS cos phi by this component. So formula P average power equal to ERMS into IRMS cos phi multiply by cos phi. So check here the angle, both the angle are 0 between the IRMS cos phi and between ERMS. So they are in the same phase. So this is called working component. Yes. This component is responsible for the power dissipation in the circuit. So this IRMS cos phi is called working component. Fine. So this component is called working component. Working component. But now again, as the phase angle between the ERMS and IRMS sine phi. Okay, now by the red pen, I'm selecting the component that is perpendicular to the EMF. Now we are talking about the power dissipation by the this one component, the red one. Okay, so here the ERMS in this direction and IRMS sine phi in this direction. So the angle between them equals to 90 degree. So again, the phase angle between the ERMS and IRMS sine phi is pi by 2. So the average power consumed per cycle in the circuit due to the component IRMS sine phi is given by ERMS multi by current component IRMS sine phi. An angle here between the both these component equal to pi by 2. So cos pi by 2 equal to 0 means average power equal to 0. Clear? Thus, average power consumed per cycle in the AC circuit is wholly due to the component that is IRMS cos phi. That's why it is called working component. Clear? So IRMS cos phi of the virtual current or IRMS. The component IRMS sin phi make no contribution to the consumption of power in the AC circuit, means there is no dissipation of power. So the current component, this one part will be absolutely wattless. That is why the current component IRMS sin phi is called the idle component. This is called idle component or wattless component of AC, and the component IRMS cos phi is called working or wattful component. Okay, so the sine component will be wattless and the cos component will be wattful. Clear? At same you have seen during when you pull a object by having some force F, so there will be two component, that is F cos theta and F sine theta. Yes or no? This F cos theta is useful to calculating the work, because work is equals to F cos theta multiplied by distance. But this F sine theta is not of any use. So this is working component or wattful component. The horizontal component will be IRMS cos phi will be working component or wattful component. Done? Okay. See the next question, students. A radio can tune over a frequency range uh, of a portion of megawatt broadcast band 800 kilohertz to 1200 kilohertz. Okay, if its LC circuit has an effective inductance of 200 microhenry, then what must be range of its variable capacitor? Okay, so here you have given portion of megawatt medium wave, sorry, it is not megawatt, medium wave broadcast range 800 kilohertz to 1200 kilohertz it is given. So first the operating frequency F1 is given 800 kilohertz, and second maximum operating frequency is given here 1200 kilohertz. So we have converted it into the simple hertz like this, and L is given 200 microhenry, that is equals to the power minus 10, 200 into 10 power minus 6 henry. We know F is equals to 1 upon 2 pi under root LC. Okay, so for F1, because L is same, so here it should be C1. So squaring both the side as you have given the frequency, so make a square of it. F square equals to 1 upon 2 square 4 pi square LC1. Make C upside and you will have the value of C1, that is equals to 197.7 into 10 power minus 12 farad, that is called picofarad. So it would be equals to 197.7 picofarad. And second, similarly C2 equals to, you will get 87.8 picofarad. Okay, just change the frequency and rest all the things are same. Fine. Okay. Okay, students. So our next topic is AC generator and AC dynamo. Actually, in the chapter EMI, we have understood the concept of the AC generator and EMI. So let us recall the concept what we have understood in during the EMI. We have seen a coil. See here, this was the north and south pole magnet, and we have seen there is a coil. Fine, there was a coil. This coil having some normal, like it is coming like this, and this normal making an angle theta with the plane of the coil. This normal of the plane is making with theta with the magnetic field. Clear, beta? So this is your angle theta. Now we know the amount of flux produced phi is equals to B dot A. So phi is equals to B into A into cos theta. Clear? Theta, as this coil is rotating by an angular frequency omega, so angle traveled by it, theta is equals to omega upon t. So, sorry. Angular frequency is equals to angular displacement upon time, theta by t. So, theta becomes equals to omega t. Clear? So, phi equals to B into A into cos omega t. Now, EMF is given by EMF is equals to negative of d phi by dt. By the Faraday's law, E is equals to minus of d phi by dt. Clear? So first we have to found d phi by dt. So d phi by dt is equals to d upon dt. Place the value of phi here. That is equals to b a cos omega t. Now b and a are constant, and here it will be d by dt of cos omega t. So B and A are constant, and differentiation of cos omega t is equals to minus sin omega t minus differentiation of cos omega t equals to minus sin omega t multiplied by omega, that is constant for the coefficient for t. So it will be carried out minus omega t into omega. So it will be equals to minus B A omega sin omega t. Fine. Yes, this is d phi by dt, d phi by dt. If there will be n terms, so the EMF will be equals to n times. So n d phi by dt equals to, here it should be n. So place one n there and you will have nb omega sin omega t. So now E is equals to minus of d phi by dt and d phi by dt. So place the value here. So E equals to negative, and here it is equals to minus nba omega into sine omega t. Now this is cancelled. So you will have E equals to nba omega sine omega t. Okay. At omega t equals to pi by 2. At omega t equals to pi by 2, your E will be maximum. E will be maximum, that is called E naught. And E naught equals to what? NBA omega sine omega t. In the place of omega t, you can place pi by 2. Now this sine pi by 2 equals to sine 90, which give the value 1. So E naught become NBA omega. Okay. So place the value here in equation number 1. You will get the final equation for the EMF. E equals to E naught sine omega t. Clear? Here E naught is the maximum value for the EMF, peak value of the EMF. Clear? Yes. Moreover, you can write like this: E equals to E naught sine omega t. So in this way, we have generated the sinusoidal voltage, and this device that is used to generate the voltage is called AC generator. Okay, if you draw the waveform of the E naught sine omega t, so as it is following the sine wave curve, so the waveform will be like this. This is the graph of sine omega t. Okay, so this angle will be omega t, and here it will be the value of EMF, and the maximum value of EMF will be taken as E naught here. Yes, so this was the principle behind AC generator. Got it? Theory of the AC generator. What is AC generator or AC dynamo? Yeah, another name of the generator is also dynamo. So actually it is a device that convert mechanical energy into the electrical energy. Yes. Okay, nowadays inverter are taken place of generators, but before inverter, generators are there. Maybe you have uh, many a times you have been seen these generator, like in conventional Indian marriages, there are generator for lightning and sound purposes are used. Yes or no? Yeah, so a big generator is also there during all marriages and there. Okay, so to give the backup. So AC generator, an AC generator dynamo is a machine which produces alternating current energy from mechanical energy, which produce alternating current energy or alternating current or voltage from mechanical energy. It is the most important application of the phenomenon of electromagnetic induction. Yes, so on what concept it is using? It is working on the concept of electromagnetic induction. Yes, we have used the formula for Faraday's law, and Faraday's law was the formula for electromagnetic induction. Fine. So it using the concept of electromagnetic induction. The generator was designed by by a Yugoslavian scientist called Nikola Tesla. So Nikola Tesla has designed this generator. Principle: an AC generator dynamo is based on the phenomenon of electromagnetic induction. When there is amount of magnetic flux linked with a coil changes the EMF induced in the coil. Yes. So it's based on the law of electromagnetic induction that says that whenever there is an amount of magnetic flux linked with a coil changes means d phi by dt, Faraday's law, then there will be the production of EMF. Okay. Okay, there will be the production of EMF. Yes. The direction of current induced in given by Fleming right hand rule. Obviously, this all we have read in the chapter EMI. Construction. So first construction, the essential part of the AC generator are. So before going to the construction, see the constructional part. First, you having the magnetic poles, south and north poles. These poles are radial magnetic poles instead of becoming flat. These are radial magnetic poles. Okay, like this. Hmm. These are radial magnetic pole for giving the perpendicular magnetic field every time to the coil. Yes. So first here is a radial magnetic pole. In between there is a rectangular coil. There is a coil in which a core was there, soft iron core were there. In that core, so many tons of copper wire will be wounded or wrapped there. Then there are two slip rings. See here, this is first connection that is connected to this slip ring. Okay, and this slip ring will slide on the first slip ring will slide on this first brush. Okay, this brush will remain itself in stationary position. Now the second leg of this one, the second leg is connected safely without of any touch to the second slip ring. Clear? Second slip ring. This is a second slip ring. Now when it is moving, then the legs as well as the slip ring will move. Okay, then these legs will move and touches the carbon brush and the supply electricity will be flow through the circuit. Clear? By using the Fleming right hand rule. Yes. Yes. See, and this is the another type of movement. After one half cycle, and after one half cycle, the direction of current will be changed. So the current will flow in another direction. Okay, these are carbon brushes. These are called slip rings, and this is external resistance. Now, and yes, first the essential part of the AC generator are first it is armature. Armature means beta coil. So ABCD is a rectangular armature coil. It consists of a large number of tons of insulated copper wire wound over a laminated soft iron core. So there is a laminated soft iron core. Over that, a large number of tires will be wrapped on round over the laminated soft iron core. The coil can be rotated about its central axis. Okay. So this coil can be rotated. Yes, like we have seen the coil here. It can be rotated. So this is the coil that can be rotated by some external power. Okay, by some external mechanical energy. So here we will give it mechanical energy from the axle of the coil and will rotate it, and the coil will convert this mechanical energy into the electrical energy. Second, after armature means coil. Second, field magnet. North and south are the pole in pieces of a strong electromagnet in which the armature coil is rotated. Axis of rotation is perpendicular to the magnetic field lines. Yes. So this is the axis of rotation about which your coil is moving, and this axis of rotation is perpendicular to the magnetic field, means magnetic field lines are passing through perpendicularly through the axis of rotation. Got it? Clear? Okay, next slip rings. R1 and R2 are the two hollow metallic rings, which are two ends of the armature coil are connected. These rings rotate with the rotation of the coil. Yes, there are two slip rings. Along when these coils are moving, these slip rings are also moving. Okay, so these rings are also moving, but there are stationary brushes. On these brushes, these rings will be touched. So these brushes will gather the amount of current and will flow from the outer circuit. Hmm. So R1 and R2 are the two hollow metallic rings. These are hollow metallic rings to which the two ends of the armature coil are connected. These rings rotated with the rotation of coil. Clear? Okay, students, see here. This is the your pole magnet. Okay, north and south pole pieces. Magnetic flux will be emitted from these pole magnet, and this is one slip ring that is connected to the this red one terminal. Fine. Yes, and here the blue one terminal will not touch the ring at all, and the blue one terminal will connect it to this another slip ring. Fine, and a carbon brush is there to convey the electric current outside circuit. Clear or not clear? Okay, so two terminals may be there. The red one becomes the first terminal, and the blue one become the second terminal. Clear, beta? Now, next, carbon brushes. What are carbon brushes? Here, B1 and B2 are carbon brushes. In the diagram, you see carbon brushes. These convey the electricity in the outer circuit. Okay, so from the two terminals or from the two legs, there will be connection of two carbon brushes. They are stationary. So B1 and B2 are the two flexible metal brushes of carbon rods. They are fixed and kept in light contact with the R1 and R2 respectively. The purpose R1 and R2 means the brush B1 is connected with the ring R1 and brush B2 will connected with the ring R2 respectively. The purpose of brushes to pass the current from the armature to the coil in the external load resistance means the current produced from the coil will be conveyed to the outer circuit. Clear? Theory and working. Okay, theory and working of the AC generator. As the armature coil is rotated in the magnetic field, the angle theta between the field and normal is coil changes continuously. Therefore, a magnetic flux link with the coil changes and an EMF is induced in the coil. Yes. So here you see the angle of theta between the magnetic lines of forces and area vector. This angle will changes. So by changing this angle with the formula of phi is equals to BA cos theta, by changing this angle, this flux will also changes. So by d phi by dt, EMF will produce on the coil. So EMF will be induced in the coil. To start with, suppose the coil is perpendicular to the plane in a plane of paper, which is the magnetic field is applied with AB at the front and CD as the back. The amount of flux link with the coil in this position will be maximum. Okay, so first you see, consider this position as given in the theory, like your coil is exactly perpendicular to the applied magnetic field. Yes, here the magnetic field blowing in the north uh, lines of forces and south here. So the magnetic field lines are exactly perpendicular to the surface. Clear? Here the lines of forces are exactly perpendicular to the surface. So that this is magnetic field vector B vector. Also the normal vector will be lying here. So the angle between normal and magnetic field equals to 0 degree. So the maximum flux will be crossed out from this plane. Say yes or no? Okay. So maximum flux will be there. Okay. So to start with, the coil is perpendicular to the plane of the paper in which magnetic field is applied with AB at a front and CD at the back. Okay, so the front here it is given AB and CD, the back portion of the coil CD at the back. The amount of flux linked with the coil in this position is maximum as the coil is rotated anti-clockwise. Now this coil is rotated anti-clockwise. Okay, anti-clockwise means opposite direction. So anti-clockwise, yes. So as the coil is rotating in this way, yes, this is axle and your coil is rotating here. Means slowly this point will turns here and this point will turns here. Okay. So after some time A will come here and B will become here. Okay. So as the coil is rotated anticlockwise, AB moves inward and CD moves outward. Obviously, this AB will move inward inside and BC will move outward. Yes. Okay, BC will move outward. Sorry, CD. CD will move outward. See, because CD is previously in outward, so it tries to come forward here in this direction. Okay, outward. The amount of magnetic flux linked with the coil changes. According to the Fleming left hand rule, the current induced in the AB from A to B and in CD it is from C to D. So here the current will be A to B and C to D. On moving, the current will be A to B and C to D. Clear, beta? Yes, the direction of current is like this: A, B, then C, D. A, B, and C, D. Clear? And in outside circuit, your direction A to B, C to D. So outside circuit, like here it is a circuit. We have connected a resistance R. So direction will be like this from here to here. Okay. External circuit current flows from B2 to B1 means brush 2 to brush 1. Yes. Brush 2 to brush 1. Check here. Yes, this is the direction. The current is moving from brush 2 to brush 1. Fine. Yes. So in the first half cycle, your current is moving brush 2 to brush 1. Fine. After half rotation of the coil, AB is at the back. Yes. Once the coil moving the half rotation, this portion AB will come at the back and CD will come at the front. Fine. Yes, AB after the half rotation, AB is at the back and CD is at the front. Therefore, the rotating further, AB will move outward and CD will move inward. Now, in next case, AB will move outward and CD will move inward. The current induced AB is from B to A. Yes, now the current will move from AB is from B to A because B goes backside. Yes or no? See here, this is A, this is B, and this is C, and this is D. Clear? So when a current is moving from A to B, on going its backside, the current will be going flowing through B to A. Yes or no? Hmm. And so current is moving AB from B to A, and in CD it is flowing from D to C. Yes, D to C. D to C. Through external circuit, now the current is flowing from B1 to B2. Okay, previously you have seen in the first half cycle, the current is flowing from B2 to B1, and now it is flowing from B1 to B2. Okay, so you can make a diagram that in first half cycle, your direction of current is in positive, and in another cycle, half cycle, your current is negative. Okay, so first cycle it is positive, and second it is negative. Fine. Yes. So, induced current in the external circuit changes direction after every half rotation of the coil. Hence, the direction of induced current is alternating in nature. Magnitude of the induced EMF in induced current. Yes, we have to find the magnitudes of induced EMF and induced current. So, we have calculated here the magnitude of induced EMF. The same derivation you have to do here, E equals to E naught sine omega t. Fine. So, like N is the number of turns of coil, A is the area enclosed with the coil, B is the strength of magnetic field, and theta is the angle with which the normal of the coil make with the B with any instant of time t. So, by the formula phi is equals to NB dot A equals to NBA cos theta, NBA cos omega t. So, as the coil is rotated, theta changes, therefore magnetic flux phi linked with the coil changes, and hence EMF induced in the coil. So at that instant, E is the EMF induced, so E equals to minus d phi by dt, that is equals to minus NBA cos omega t. NBA cos omega t, I mean minus NBA, we have taken the common differentiation of cos omega t become minus sin omega t into omega. This minus and minus sign get cancelled out, and this is equals to NBA omega sin omega t. So the induced EMF will be maximum when sin omega t will be maximum So E max equals to E naught NBA omega multiplied by the maximum value of sine omega t equals to 1. So finally you have E equals to E naught sine omega t. If you plot the diagram versus omega t or versus t, so you will have the AC alternating EMF like this. Okay. Before now we also make this diagram, made this diagram at the start of the chapter. Yes or no? E naught T by 4, here it is maximum. At T by 2, your current will be 0 or EMF will be 0. Then it is 3T by 4, and after one cycle, current and EMF also repeats its value to 0. The current supplied to the AC generator is also sinusoidal. Now, this is alternating EMF. We have got E equals to E naught sin omega t. And you know I equals to E by R. I equals to E by R. So I equals to E, the value of E equals to E naught sin omega t divided by R. So E naught upon R becomes I naught sin omega t. Clear? So E naught upon R it becomes I equals to I naught sin omega t. So this is the value of maximum value of the current. Okay. And if you plot the graph of current, so it will having the same value like this. I equals to I naught sin omega t. Fine. Only the peak will be taken the value of I naught. Done.